Hello and welcome back to this NPTEL course on thermal physics. In today's lecture, we will be talking about mean free path. Now, why it is important to discuss the collision and mean free path in a molecular gas assembly? So, the situation is something like this. Let us say I am standing or I am inside a room in one corner of the room and I have a bottle of perfume, something like a deodorant or could be a bottle of some other perfume, whatever, and you are standing on the other corner of the room, which with our mutual distance is something like of the order of 5 meters or 10 meters maybe, depending on the size of the room, but it is of the order of meters. Now, in the last week's lecture, what we have seen is the mean velocity of a gas assembly at room temperature is of the order of 300 meters to 500 meters per second. We have computed it for oxygen. I remember the numbers were of the order of 400 meters per second. Depending on the molecular mass and other temperature, room temperature can also fluctuate. It will be somewhere between 300 and 500 meters per second, average speed. Both all the three, like mean speed, the RMS speed, the what was it, most probable speed, or everything was of that order. So, when I open the bottle of perfume in one corner of the room, what happens? The gas particles evaporate from the surface. Okay, they are not exactly monomeric particle, but nonetheless they are gas particles. Okay, and these gas particles, let us assume that they have average velocity of 200 meters per second, very low compared to other elemental gases. But even if with that speed, in order to cover a distance of 5 meters to 10 meters, it should take less than a second, a fraction of a second. So, when I open the bottle of perfume, you should smell it almost immediately. But in reality, what happens? It takes a finite time, depending on let us say the room is totally closed, there is no flow of air, it will still reach you, but maybe depending on the situation, maybe in 15 seconds, maybe 20 seconds, maybe sometimes a minute, it will go to it will reach you. So, the gas particle which I am releasing at one corner of the room is taking a much longer time and as opposed to what predicted by kinetic theory to reach the other corner. Now, what does it mean? So, Clausius first came with the hypothesis that it is because this is happening because the gas molecules are not taking a linear path. They cannot take a linear path. There are collisions, and of course, this is one of the prime assumption of kinetic theory that there are collisions between gas molecules. Collisions are elastic, they are colliding with themselves, they are colliding with the wall, container of the wall, and they give rise to pressure. So, at first we will be just considering the collision among themselves. Okay. So, when this happens, the gas molecules they are bound to take a zigzag path. So, they cannot go from one end to the other end of the room uninterrupted. They have to suffer many different collisions, but still they make a progress, primarily because in this case, because see, the perfume is one type of molecule which is not present in the room before I open the bottle. Moment I open the bottle, there is a finite density of perfume molecules in one corner, and in order to gain equilibrium, they have to disperse throughout the room and finally it has to be equilibrated. So, this is something that we will be discussing later on in a more elaborate manner when we will be discussing diffusion. This is something called molecular diffusion. Okay. But in the path, they are constantly suffering collision, and that is why it is important to compute something called the mean free path of a gas molecule for a given gas assembly. Okay. So, let us come to this let us take it up in a more systematic manner. So, we are here, the black dots represent the gas molecules in some arbitrary gas assembly. Now, what we have done here, we have just tried to trace the path of one such molecule, which is, let us say, starting from here, it will go here, then take another collision, go there, take another collision, in this direction this will take another collision, and it will keep moving like this, and in between collision it will transverse or travel a path x1, x2, x3, x4, x5, x6, 7, 8, so on and so forth. It will keep moving all the time. So, let us assume that somehow we manage to tag one gas molecule and I can very accurately measure the distances x1, x2, x3 up to a certain number. Okay. And let us say altogether I have n such numbers, nc such numbers, nc being the total number of collision. So, finally, we have to have x nc. Now, the average distance travelled between two successive collisions, the average for this tagged molecule will be the average of all these numbers. So, x1 plus x2 plus x3 all the way to x nc divided by nc, nc being the total number of collision, total number of collision. Right. And if the molecule travelling, and please remember that this molecule, every collision will change its velocity, change its speed actually, velocity in a sense, because it will change both the direction and the magnitude of the velocity. So, what we can do is we can compute, if we start from this position and end here, let us say. So, the overall time taken by this molecule, if we for NC number of collision is t, then we can compute, and the total distance that has been travelled is something, some x prime or something, then we can calculate the average speed c bar of this molecule, right. So, for this particular molecule, what we can do is we can write the x average as c bar times t divided by nc, which is c bar times tau. What is tau? Tau is t by nc, t being the total time taken and nc being the number of collision. So, tau is the average number, average time taken between two successive collisions. So, that is how we can compute the mean free path of the tagged molecule. But this is only for one molecule. In the gas assembly, we have typically Avogadro number of molecules, 10 to the power 23 number of molecules, right. So, for each such molecule, if we can compute the the free path and then we take average of that, then we get the mean free path for the entire gas assembly, and that, let me tell you, it's a humongous task. I mean, you already have an idea, I mean, what I am talking about. I mean, this is absurd, this is okay, sorry, just a minute. So, this is absurd, I mean, we cannot do that. So, instead what we can do is we can kind of formalize it in a more systematic manner. So, so what we can do is, in a gas assembly, we can define dN1 as the molecule with free path between x1 and x1 plus dx1. dN1 is the number of molecule in this range. dN2 similarly is the molecule with free path between x2 and dx2, and so on. So, the mean free path, by definition of mean free path, will it will be x1 dN1 plus x2 dN2 up all the way to xn dxn divided by dN1 plus dN2 plus dN3 all the way to dNn, and so on. So, the integration, I mean, because if the numbers are large, number of such assemblies are large enough, we can replace this summation with an integration, and we can write the lower one will be the total number of molecules. In this case, we are just writing it n0. There is a reason for it. Instead of n, we are writing n0, because we will be later on introducing n in a slightly different way. Then it will be integration x dn, and the integration limit is 0 to L. Now, why L? L being the typical dimension of the container. The gas molecules are inside some container, some tank or something. So, if it has a dimension of 1 feet by 1 feet by 1 feet, the maximum value of x can be only 1 feet or maybe the diagonal length, whatever it is, but it is of the order of L. Now, we shall see later that the mean free path for a standard gas assembly, which is, let us say, some elemental gas at STP, that is standard pressure and temperature, this is very small as compared to the length of the container typically. Okay. So, just to put things in perspective, the typical length of the container is of the order of 1 meter, or let us say 0.1 meter, whatever. 1 meter, of the order of that. It could be less than that, it could be more than that, and the mean free path we will see that it is of the order of 10 to the power minus 7 meters, 10 to the power minus 8 meters, which is tiny. Okay. So, for all practical purpose, we get lambda is much less than L, and the upper limit of this integration in effect becomes infinity. So, the integration lambda is actually integration 1 by n0, 0 to infinity x dn. So, this is the integration we have to compute in order to find out lambda for a gas assembly. Now, so in order to compute this integration, this is only theoretical up to this point. In order to compute this integration, what we have to do, we have to get an expression for dn in terms of x, right. So, how do we do that? And similarly, okay, and before we go there, similarly the mean free time can also be computed in a similar manner as tau is equal to 1 by n0. Please remember, it is not for one molecule, but the mean free time, or actually probably I should, what I should do is, I should not confuse you by writing tau here. I should write T bar for a single molecule, then I think you get a better feel, right. So, this is T bar, and x bar for one molecule, T bar for one molecule, lambda for the assembly, similarly tau is for the assembly. So, tau will be averaging over all these T bars, which is nothing but 1 by n0 integration 0 to L by C bar being the average speed of the assembly, which we get from the Maxwell's distribution anyway, and T dn, right. So, once again, as tau becomes very less compared to this quantity L by C bar, we can write this as 1 by n0, 0 to infinity T dn. So, either way, in order to compute lambda and compute tau, we have to find out a way of determining dn x or dn as a function of t. Okay. So, in order to to that aim, what we do is we start looking into this physical picture. We have a gas assembly, let us say it is open, okay, and we just, so it is exactly like the perfume bottle. Moment you open the perfume bottle, the fragrance molecules, the perfume molecules get released, okay, and they are traveling across the room. Now, they initially start off as a group, as a big group, because I get the strongest smell, of course. If I have the bottle in hand, I get the strongest smell. So, there are the number density is maximum. As they travel across the room, travel across the atmosphere, they start colliding with each other among themselves, and there are molecules that are knocked out of that group. And so, this is again this is not the best model to describe a physical system, but this is where we start, okay. And as they travel, they start losing molecules due to collision. So, let us say they start with a number n0 to begin with, okay, here, and finally they end up after a distance x or a time t, they end up having n number of molecules, which is n0 multiplied by some function of either x or t, because as we see, if we look at the gas assembly, we immediately after that, when the x or the t is very small, okay, then n is approximately equal to n0, but as we go away from the initial position, or as we go advanced in time, n becomes small compared to n0. So, f is the function that to be determined. We do not know what is x. Now, what we do is we define, and so basically what we realize from there, that f has something to do with the collision probability, okay. So, we have to have, we start with n0 number of molecules in an assembly, and then we multiply this with f, which is a function equivalent of with a function, and then get n number of molecule that still survives presumably without a collision in this assembly. So, basically f is a function that's a probability that says that gives you the probability that a molecule travels a distance x without suffering a collision in that assembly. Okay. So, please understand this, because n0 multiplied by f gives you n, which is still existing, still surviving in this assembly. F is essentially the probability of not suffering a collision over a distance x. So, we are just computing f x for now. Similar manner we can do it for f t also. I will just show you how to do it for f x. Same logic, same type of calculation you can apply and you can find out f t. But later on we will see that f t is not needed separately. We can do that, of course, but we will see later that tau and lambda, they are strongly correlated to each other. So, we can either work with f t or either work with f x, any of this will do. Anyway, now at the same time we introduce a new parameter p x dx, where p x is actually the probability that a molecule, the p x dx is actually the probability that a molecule do suffer a collision in this interval x to x plus dx. Okay. Okay. So, let me try to explain this in more detail. So, we have where is it? Yeah, we have this gas assembly, they are colliding, right. Let us say this one collides with this one and gets knocked out, right. What is the probability that it will suffer a collision in this distance? The probability is given by p x dx. What is the probability that it will not suffer a collision? This is given by a probability 1 minus p x dx, right. That is the, because the total probability has to be 1. Right. Now, the function f x talks about probability of not suffering a collision of the up to a distance x. So, the function f x plus dx is the probability of collision that it will the probability of not suffering a collision up to a distance x plus dx. Now, what will be that? That will be a product of f x multiplied by 1 minus p x dx, because f x is not suffering a collision up to x and this one is not suffering a collision for next dx. Okay. So, the probability that is f x plus dx, that is not suffering a collision up to x plus up to a distance x plus dx, is a product of f x and 1 minus p x dx, right. So, this is exactly what we have done here. Oh, this is exactly what we have done here. F x plus dx is f x into 1 minus p x dx. Now, we expand f x plus dx in a Taylor series only up to the first term, then we simplify f x cancels out, we have df dx is equal to minus p x f x, which on integration gives you f x is equal to a e to the power minus p x x, right. Now, we have to realize that f 0 at x equal to 0, f is equal to 1, because the place where we start, we have n0 number of molecules. Go back to this picture, at x equal to 0 or t equal to 0, f has to be equal to 1, right. So, there is no collision, no at the beginning or at the initial distance there is no collision, total number is equal to n0. So, n at x equal to 0 is equal to n0, right. So, that gives you a equal to 1. So, the function f x is simply e to the power minus p x x. P x is undetermined at present, we do not know what is p x. So, we write f x n x is equal to n 0 f x. Similarly, n t also we can write n 0 f t, where t has to be determined. We can do that in a similar manner, just the way the same treatment can be applied for time also. So, n 0 e to the power minus p x x. Now, we compute d n. What is d n? d n is minus n 0 p x e to the power minus p x s d x. So, the number we are interested only in the magnitude, and this magnitude will be this without the negative sign here. Now, let us go back to the expression for lambda. Lambda is equal to 1 over n 0 0 to L x d n. We already have computed an expression for d n. We just plug it in here, right. We simply plug it in here and we get lambda is equal to 1 over n 0 0 to infinity n 0 p x x e to the power minus p x x dx. Substitute y is equal to p x x and you will find out that this simplifies to p x by p x square integration 0 to infinity y e to the power minus y dy, right. So, why it is right, fantastic, yeah. So, lambda is equal to 1 over p x integration 0 to infinity y e to the power minus y dy. This is a standard integral, you can find out this integral and it will give you 1. So, lambda is equal to 1 over p x. If you compute this integral, you will see that it will give you 1 only, right. So, finally, we get the full expression for f x, which is f x is equal to e to the power minus x by lambda. So, n x is equal to n 0 e to the power x by lambda, which we call the survival equation. This gives you the number of molecule that will survive in a group even with collision over a distance x, and lambda at present it is undetermined. We have used the used the definition of lambda, the mean free path, in order to find out the survival equation, but we have not derived lambda yet. Lambda has to be determined in a different manner. Similarly, for time, as I have said, the exact same treatment is valid for time also. So, we can always define a probability which is the probability of collision in the time t to t plus dt, and then we can find out the probability and we can find out that f t, the function that says the survival function f t is nothing but e to the power minus t by tau, okay. That p t will be equal to 1 over tau, and the survival equation for time will be n t is equal to n 0 e to the power minus t by lambda, t by alpha, t by tau, right. Now, if go back to let us go back to this relation here. You see x bar is equal to c bar t bar, right. In the similar note, we can say that lambda is equal to c bar tau. So, our job we have to determine lambda, but before that let me introduce something, a new parameter called the collision cross section. Now, what is a collision cross section? Let us say a molecule is travelling through space, okay. Now, if a molecule is travelling through space, it will collide with other molecules, and then we can define something called the collision cross section, which gives a effective cross section that this molecule have when it is travelling through space. Now, at present at first glance it seems like that this collision cross section is exactly like the cross section of that molecule, but later on we will see that there are it is not exactly that, but that is something to do with the cross section, the actual cross section of this molecule, but it is sometimes more than that. We will come back to that in the next lecture, but for now what we are going to do is we are just going to assign a collision cross section and we call it sigma, okay. We just name it sigma. Now, once again we are looking into a tagged particle. We assume this is a 0th order approximation, okay, in which we assume that only the tagged particle is moving through space, all other molecules are stationary. Now, this is a very bad approximation. I can tell you, I mean, it is not nowhere close to the actual picture, but this is a 0th order approximation. That is where we start with. Slowly and slowly we will build on that. Okay. Now, let us say this molecule is moving with a speed c and it has a collision cross section sigma. Now, in a small time interval dt, how much will that move, or what is the volume swept by this particle? Let us say this is my collision cross section, c is the speed of the molecule and it is travelling a length c dt in the small time interval dt. So, the volume that is swept is nothing but dV is equal to sigma c dt. Right. Okay. So, this is the volume inside this cylinder here. Now, if and only if there is another molecule present in this volume, there is a collision. If there is no molecule present, there is no collision. But assuming that there are sufficient number of molecules present, so that there is a collision inside this volume, the total number of collision has to be proportional or has to be a function of the density of the molecule as well, the density of the gas assembly as well, right. So, that is why we get, if n is the density of the number density of the gas molecules, and please do not confuse it with the number of moles. So far we have used n only for number of moles, but in this treatment n is the number density of molecules. So, that means if we have n number of molecules, with a volume V, so n is simply capital N by V, right. So, the probability of having a collision in the time interval dt is equal to n c sigma dt. Why n c sigma? This volume is sigma c dt, right. Actually I should change the order of this. It will be sigma c dt, then it will be sigma, or rather I would just write dV here, and dV is equal to sigma c dt, and n being the number density. So, how many collisions in this interval, this small time interval? That is exactly sigma c dt times n. Okay, that is the number of particles, the other particles that is present in this volume, which is travelled or which is covered in the small time interval dt by this one molecule we are talking about. So, and this is nothing but Pt dt. Please remember what was in our treatment, what was Px dx, that the probability that a molecule do suffer a collision in this interval x to x plus dx. Similarly, Pt dt is the probability that a molecule do suffer a collision in the interval t to t plus dt. So, they are basically the similar parameters, one in space, the other one is defined in time. Okay. So, this is nothing but, and we see that dt cancels out from both sides, and we have Pt is equal to n c sigma, which is equal to 1 over tau, as we have seen Pt is equal to 1 over tau. We have not computed that explicitly, I will just leave it to you for that computation. The way we have proved that lambda is equal to 1 over x, similarly we can prove that Pt is equal to, or tau is equal to 1 over Pt, or Pt is equal to 1 over tau, right. So, then we get a relation tau is equal to 1 over n c sigma. Now, what is this c? C is the speed of the molecule, speed of the tagged molecule, right. So, we get a relation, and we remember that lambda is equal to c bar tau, we just wrote that here, right. It has to be the relation. So, we get lambda is equal to c bar n sigma by c. I have written c in red just to make it distinct from c bar being the mean velocity. C is something, Okay. So, now the question is, what is C? What is an appropriate expression for C? Is it exactly similar to this mean velocity C bar here, or it is something else? So, we will start here from the next class, and we will compute an expression for C under the first order approximation, the second order approximation, and we will find out a proper expression for the free path. Okay. So, that is where we stop today. We will continue from here in the next lecture.